Hello and welcome here at BASF booth of K-Fair 2019. I'd like to welcome everyone to the second tech talk of today. It's now 2 p.m. and I have Raphael Dabu from the Regional Application Center of Plastic Additives here with me. Raphael, welcome.
Many thanks.
He will be talking... Sorry?
Hello.
Hello, hi. He will be talking about recycling of polymers based on non-halogenated flame retardants. So Raphael, stage is yours. Have fun.
Okay, many thanks, Alexander. Hello, everyone. So as Alexander says, I'm Raphael Dabu from Regional Application Center at Plastic Additive at BASF. And I will show you the results of a study on recycled halogen-free flame-retardant polymers. This study was carried out by Fraunhofer Institute in Germany. So, do you hear me? Yeah. So, how does mechanical recycling takes place typically in Germany and typically for E&E equipment? E&E meaning electrical and electronic devices. So as you can see, most of the stuff is incinerated. Only a small fraction gets collected, grinded, as you see here on the circle, reprocessed until new E&E equipment can be produced again. So the question was raised whether HFFR polymers, so halogen-free flame-retardant polymers, can serve to support the mechanical recycling, so the closed-loop recycling. And for that, a specific multi-year study was conducted at the Fraunhofer Institute LBF in Germany. So it means Institute on Structural Durability. And it was also supported by PINFA-Association, so phosphorus, inorganic, nitrogen, flame-retardant association. Okay, so what was done in this study? So the result will focus on two main systems, so polypropylene plus flame-stab NOA116 at 0.5 to 1%, and on polyamide 6 plus melamine cyanurate with loading around 10%. And for both systems, two main pathways were followed. On the left-hand side, multiple extrusion was carried out, up to 5 extrusions. Yeah. And after that, the extruded pellets were either injection molded, in the case of polyamide, or cast film was made with polypropylene. And after that, of course, the specimens were characterized, so mechanical properties and flammability. And on the right-hand side, so the second path, so oven aging was carried out, and in two different ways. Either the pellets, so they were compounded first, of course, and the pellets were first aged, and then the oven-aged pellets were either injection molding for polyamide or cast film were made. And we also made the other way around. So first producing the specimens, and then the specimens were over-aged. And at the end, of course, again, measurement of the properties, especially flame retardancy. So that's the way it took place. Okay, now to the result. First, polypropylene, multiple extrusion. The flammability test was a vertical test, according to DIN 4102 Part 1. It's a test carried out on a film, in this case 200 micron thickness, wherein the maximum burn height must be not higher than 150 millimeter after 20 seconds. That's an example here that you have on the picture. And you can see on the left-hand side on the graph that after 5 extrusion, the flame retardant performance is absolutely maintained. So it's a nice result. And we saw that the melt flow index and that yellowing tend to increase over the extrusion, which is normal. But the mechanical properties and the optical properties were nicely maintained. That's important. Okay, still to polypropylene, now oven aging. So you can see by yourself that oven aging after 80 days at 120 degrees, which is a lot for polypropylene, and you have no change of the flame retardancy, and the performance is also nicely maintained, either whether the aging took place on the films or on the pellets. In this case also, the melt index tends to increase. A certain yellowing took place after oven aging, which is normal in a way. Further results. Now I pass to polyamide, multiple extrusion. In this case, okay, it was injection molded parts, and the flammability test was the well-known UL94. So a vertical test, again, where the V0 level had to be achieved. So quickly said, as you probably know, V0 means stop burning after 10 seconds, and the falling droplets must not ignite a cotton piece placed underneath. So that's what it means. And as you can see by yourself, also V0 was maintained after 5 extrusion. And in this case also, molecular weight tend to be reduced, and also yellowing partly took place. And in the case of polyamide 6, the mechanical properties were partly reduced also. Okay. Still with polyamide 6, now oven aging. In this case, we went over lab scale test in the sense that we received a post-consumer scrap from 2 different companies. So something already realistic. You can see supplier A, and B. And the oven aging took place at 120 degrees during 40 days. And you can see that the V0 level was also maintained in this case. Okay, so finally, it appears that halogen-free flame-retardant polymers contribute to mechanical recycling. We could see that it was demonstrated that the flame-retardant performance, either of polypropylene plus flame-stab NOR116 or of polyamide 6 plus melamine cyanurate, is maintained over multiple extrusion and over oven aging. Yeah, and in the case of polyamide 6, we could also see that it was also valid for post-industrial scrap. Yeah. And in addition, it's known for a fact that antioxidant provides good stabilization. And it was also validated in this study. Also, and you can even better have retention of the mechanical, rheological, and color property by adding antioxidant over the subsequent processing steps. Okay, so in conclusion, halogen-free flame-retarded polymers support a circular economy, you can say that, and they also support the measures stipulated in the European directive on waste of electric and electronic equipment, and also on the so-called European Eco-Design Directive. Okay, I would like to acknowledge again the work carried out by Fraunhofer Institute in this work, and many thanks for your attention.